Now let's look at the second characteristic, which we call chemical shift, and it talks about the location of signals in the NMR spectrum. So for example, in this spectrum, we have 5 signals. 1, 2, 3, 4, and 5. This little broad peak right here, this is also a signal. We are going to talk about it later. So the location of each signal will be defined relative to the signal for a compound which we call TMS, or tetramethylsilane. So a tiny amount of TMS is added to the NMR solvent, and it will show a peak at the very right of the NMR spectrum, so we count it as a reference and we label it as 0. And then we define the location of other signals relative to that. So we show their locations by these numbers. For example, this signal right here, it appears at around 1.2 ppm. So the unit for chemical shift is ppm, or parts per million. Normally we see that from 0 to 12 ppm, but majority of the signals appear between 0 to 10. The only signal that can appear at 12, I can say, is OH in carboxylic acid. Other than that, most of the signals appear between 0 to 10 ppm. There is a terminology that we use a lot in NMR. So if a hydrogen appears at lower ppm, we call that upfilled. So it's kind of opposite of what you think. If I say this signal moves upfield, that means it appears at lower ppm. And if I say the signal moves downfield, that means it has higher ppm. So just be very careful of these terminologies. So alkane protons generally give signals around 1 to 2 ppm. Now if we replace one of the protons in alkane with an electronegative atom such as halogens or nitrogen or oxygen, the chemical shift for these protons will be shifted downfield or to the higher ppm. You can even compare the values here. So the reason for it is the inductive effect of these electronegative atoms. So for example, iodine is more electronegative than hydrogen. Therefore, it will pull the electron density towards itself, which causes these hydrogens in methyl to be surrounded by less electron density, and we call them, they become more deshielded. And deshielded hydrogens appear at higher ppm. So the more electronegative the atom, that inductive effect would be stronger, and we are going to see these protons appearing at higher ppm. Fluorine has the strongest inductive effect, and as you can see, the chemical shift increases here. Now, something I would like to mention here is that you don't need to memorize these chemical shifts for specific molecules or compounds, but you need to know the range of basic values for chemical shifts in the final exam, and we are going to talk about those values in the following slides. Now, when we have more than one halogen, this effect is additive. So for example, here with one chlorine, the chemical shift for these hydrogens is 3.1 ppm. Now if we add another chlorine, the chemical shifts for these hydrogens will be at 5.3 ppm, and with 3 chlorines it's at 7.3 ppm. So basically each chlorine atoms adds about 2 ppm to the chemical shift. Another important point here is that the inductive effect tapers off with distance. So if we have chlorine attached to alpha carbon, these alpha protons appear at higher ppm comparing to the beta protons. And I can say even the protons in gamma are almost unaffected by the chlorine. So here is the table for the chemical shifts. This is the table about the basic numbers for chemical shifts that I was talking about. I'm not going to ask you about these numbers directly, meaning that I won't ask you what is the chemical shift for an aldehyde proton or what is the chemical shift for an allylic proton. But pay attention. But You need to know these numbers in order to read through the hydrogen NMR spectrum. So you should have some ideas where do you expect to see these signals corresponded to each of these functional groups. Now I'm going to review this table and give you some shortcuts to remember these numbers. So let's start with the first functional group, which is alkane functional group. So these hydrogens, all of them, they are connected to the sp3 hybridized carbon, and there is no electronegative atom connected to that carbon. So alkane functional group, you should expect to see their protons peak between 0.9 to almost 1.7 ppm. So as I said, these numbers are in just the range. You may find different ranges, like for example 0.5 to 1.5 or 2 ppm. That shouldn't be very accurate. You should see and know the approximate position of each functional groups in the hydrogen NMR spectrum. So alkane appears between 0.9 to 1.7 ppm. Then we have allylic hydrogen, which is the hydrogen connected to the carbon, which is connected to the double bond. Or even this hydrogen, it's the same thing, right? So it's similar to allylic. Hydrogen connected to the carbon, which is connected to the double bond. So they usually appear, we call them allylic proton, and you can expect to see them somewhere between 1.5 to 2.5 ppm. So as I said, the number that I'm giving you may not be exact the same as the textbook. I'm giving you the range, so that would be easy to remember. Then we have hydrogen connected directly to the triple bond, to the alkyne, and hydrogen connected to the carbon, which is connected to the aromatic ring. You should expect to see them at around 2.5 ppm. Now, after this region, we have the most important one, which is hydrogen connected to the carbon, which is connected to the electronegative atom. And that X, that electronegative atom, can be fluorine, oxygen, nitrogen, chlorine, bromine, and iodine. So once again, you can expect to see this proton, which is connected to the carbon, and that carbon is connected to one of these electronegative atoms to appear somewhere between 2 to 4 ppm. So here we have somewhere between 2 to 4 ppm. Sometimes you may see that it is reported as 2.5 to 4.5. So as I said, these numbers are just approximate. They are not accurate numbers. Now for the alcohol can appear between 2 to 5 ppm. I'm going to talk about that specifically in the following slides. The next important functional group is the hydrogen that is connected to an alkene. Hydrogen connected to the double bond. So you expect to see that somewhere between 4.5 to 6.5 ppm. The next important one is the hydrogen that is connected directly to the aromatic ring. Okay, this is the aromatic ring, and hydrogen directly connected to that appears somewhere between 6.5 to 8 ppm. Aldehyde generally appears at 10, and acid appears at 12. So I'm going to rewrite all of these in a more clean way. So we have alkane, so protons connected to sp3 hybridized carbon, we expect to see them between 0.9 to 1.7 ppm. Then we have these type of protons. We expect to see them somewhere between 1.5 to 2.5 ppm, almost close to 2 ppm. Then we have hydrogen connected to triple bond, and hydrogen connected to the basically aromatic methyl. We expect to see them at around 2.5 ppm. Then we have hydrogens connected to the carbon, which is connected to the electronegative atom, and those electronegative atoms can be fluorine, chlorine, oxygen, nitrogen, chlorine, bromine, and iodine. So we expect to see that somewhere between 2 to 4 ppm. Sometimes you may see that it appears more than 4 ppm at around 4.5 as well. Then we have hydrogen connected to the double bond, 4.5 to 6.5 ppm. We have hydrogens that are directly connected to the aromatic ring. So be very careful not to confuse this hydrogen with these hydrogens. This hydrogen is directly connected to the ring, but this one, they are connected to the carbon, which is connected to the ring. So be very careful not to confuse them. So we expect to see them between 6.5 to 8 ppm. Then we have aldehyde at around 10 ppm, and carboxylic acid at around 12 ppm. So these are the basic numbers. Sometimes the structure of the R group can influence these numbers. So for example, if you have an electronegative atom connected to this benzene ring right here, for example, that can influence and can shift the chemical shift for this hydrogen to the higher ppm. We already talked about it, that electronegative atoms have inductive effect. But overall, you need to know and have some idea about these functional groups and their chemical shifts. Now let's look at the example and see how can we use these chemical shifts. So okay, so I'm gonna draw all the hydrogens. Alright, so first thing first, let's decide how many signals can we see for this structure. So these two methyl groups, they are the same because we have free rotation about this bond, so they can interchange. Therefore, they have the same chemical environment. Therefore, both of them and their hydrogens will show one signal. Then we have this hydrogen, it will show another signal, And then we have these 3 protons. They also show another signal. Now let's decide about their chemical shifts. So for these sets of protons, if you look at them, these hydrogens are connected to the carbon, and that carbon is not connected to any electronegative atom. This is a sp3 carbon, so these hydrogens are alkane hydrogens, and we expect to see them somewhere between 0.9 to 1.7 ppm. Now if you look at this hydrogen, so this hydrogen is connected to the carbon. That carbon is connected to 2 R groups, but it is also connected to the electronegative atom. So we just talked about it. Hydrogen connected to the carbon and connected to the electronegative atom. So we expect to see this one somewhere between 2 to 4 ppm. And this oxygen is actually really electronegative, so we mostly see this hydrogen closer to 4 ppm rather than 2. And then we have these protons. So again, these hydrogens are connected to the carbon, and that carbon is connected to the double bond. So look at here, it's right here. Hydrogen connected to the carbon, which is connected to the carbonyl. So we expect to see that somewhere between 1.5 to 2.5 ppm. So the next characteristic is integration, which gives us the area under each signal, and that tells us how many hydrogens are there for each signal. So this is normally represented by a step curve such as these. So these integration values will be given to you. So the computer calculates the area under each signal and then displays the area as a numerical value. So you can see these numerical values here. Now, these numbers only have meaning when they compare to each other. Now, in order to convert these numbers to the useful information, we will take the smallest number and divide all integration values by that number. So here in this spectrum, the smallest integration value is 27. So we need to divide all of these numbers by 27. And doing so, we are going to get these numbers: 1, 1.48, 1.05, and 1.56. Now my question for you is that, can we have half proton? No, we cannot have 1.5 proton. So we need to convert these numbers to the whole number. And in order to do so, we need to multiply each number by 2. That gives me 2. 2.96, 2.1, 3.12. Now we need to basically round these numbers. So 2 is 2. If I round this, I'm gonna get 3, 2, and 3. So these numbers actually gives me the number of hydrogens corresponded to each signal. So this signal has 2 hydrogens. This one is 3 hydrogen. This is 2 hydrogen, and this one is 3 hydrogen. Now what this tells us is that if we have a structure and we have CH3 group in that structure, the peak for that CH3 group should be either this one or this one, because these two signals show 3 hydrogens. And if you have CH2 group in that structure, the peak for that should be either this one or this one, because they have 2 hydrogens under this signal. So this gives us the clue that which hydrogen is with which peak. Now, a good news here, in the exam, you don't need to do all of these math part, okay? I'm gonna give you the final values, either these values or the basically round off values. So you don't need to do these math part in the exam. Now let's look at this structure again, 3-pentanone. So we looked at it before. We know that there is two signals there because there is a symmetry in this molecule. So if you remember, there was a symmetry here and we had two signals for this molecule. Now we want to decide which signal belongs to the blue hydrogens and which one belongs to the red hydrogens. So in order to do that, we can look at the integration values. So the integration values here are 32.5 and 48. So what we can do, we need to divide these two values by the smallest value, which is 32.5. 48 divided by 32.5 gives me 1.47. Now we don't have half hydrogen, so we need to multiply both of them by 2. So I'm gonna get 2, and here I approximately get 3. Now these are the whole numbers. However, if you add up these two numbers, we are gonna have 5 hydrogens overall, right? But if you look at the structure, in the structure we have 10 hydrogens. So what we need to do, instead of multiplying by 2, so I'm going to rewrite all of these again. So instead of multiplying by 2, we need to multiply by 4. So we are going to get 4 hydrogens and 6 hydrogens here. Okay, so now 4 plus 6 is 10. That matches the number of hydrogens in the molecule. So this gives me this signal, 32.5. That gives me 4 hydrogen, and 48 gives me 6 hydrogens. So basically this signal belongs to CH3 groups. So overall 6 hydrogens here, and I have 6 hydrogens here. And this signal, which has 4 hydrogens, belongs to CH2 groups. Now I can assign these signals using chemical shift values as well. So if we look at blue hydrogens, this hydrogen is connected to the carbon, sp3 carbon, and that carbon is not connected to any electronegative atom, so it's an alkane, and alkane hydrogens appear at around 0.9 to 1.7 ppm. Now for the red hydrogens, so these hydrogens are connected to the carbon, which is connected to the carbonyl group. So we expect to see them at around 1.5 to 2.5 ppm. Majority of the time it is about 2 ppm, but it depends on the structure. Now if we look at this signal appears at around 1.1, so which is within this range. And if we look at this signal, it appears at around 2.4 to 2.5, which is within this range. So with the chemical shift, we can even assign these signals. So this signal belongs to CH3 groups and this signal belongs to CH2 groups.